Today, we're diving into something pretty amazing: the invisible protectors that keep our world and our bodies in perfect balance. We're talking about chemical buffers.
Okay, so let me ask you something. You can chug a big glass of acidic lemonade, right? Or eat all sorts of different foods, and yet your body just handles it. Ever stop to think about why your insides don't just, go completely haywire?
Well, the answer is this incredible chemical balancing act that's happening all the time. So, let's get right into it.
So, what is a buffer really? I mean, what are we talking about here? The simplest way to put it is this: it's a solution that just flat out resists changes in pH. It's like a chemical shock absorber. You can throw a bit of strong acid or a strong base at it, and it just holds the line. It keeps things stable.
So how do you actually make one of these chemical bodyguards? Well, the recipe is surprisingly simple. You just need a chemical tag team. You take a weak acid and pair it up with its partner, what we call its conjugate base, which is usually a salt. A really common example is acetic acid. Yeah, the stuff in vinegar mixed with sodium acetate. Or you can flip it. You can use a weak base, like ammonia, and pair it with its partner, the conjugate acid. The magic, the real power, is in that specific pairing.
Okay, so we know what they are and what they're made of. But now for the really cool part. How in the world do these simple mixtures actually fight back when things get wild?
The best way to really get this is to see it in action. So let's walk through a little experiment, based on the numbers right out of the textbook. All right, picture this. We've got two beakers side by side. One is just a regular unbuffered solution. The other one? That's our buffer, our little chemical guardian. And here's the key. They both start at the exact same pH, 4.74. Now, we're going to add the same amount of a really strong base to both of them. Any guesses what's about to happen?
And wow, the results are just night and day. Look at this. The unbuffered solution, its pH absolutely skyrockets from 4.74 all the way up to almost 11. That is a huge, massive change. But our buffered solution, it barely even moved and went from 4.74 to 4.75. That's it. That tiny, tiny difference, that's the whole magic of a buffer.
Okay, so how on earth did it pull that off? It's actually a really simple and kind of brilliant defense strategy. Remember that chemical tag team? Well, if a strong acid comes along, the weak base part of the team jumps in and neutralizes it. If a strong base attacks, the weak acid component takes care of business. The buffer basically grabs that powerful intruder, that chemical bully, and transforms it into something much, much weaker, which, guess what, has almost no effect on the overall pH. It's genius.
Now, this is way more than just a neat lab trick. This is happening inside of you, right now as you're listening to this. So let's talk about the most important buffer there is, the one in your own blood.
And seriously, I'm not being dramatic. That buffering action we just saw in the beaker, that's literally one of the fundamental things keeping you alive. All right, here's the number you need to remember: 7.4. The pH of your blood is kept incredibly close to 7.4. And that's not like a general guideline. It's a non-negotiable biological rule.
And just to show you how high the stakes are, listen to this. This is straight from the source material. pH changes of 0.4 or greater are likely to be fatal. Think about that. A tiny shift down to 7.0 or up to 7.8, and that's it. Game over. That is an unbelievably narrow tightrope to walk.
So, who are these guardians patrolling your bloodstream? Well, the main one is called the carbonate buffer system. The weak acid is carbonic acid, and its partner in crime is the bicarbonate ion. This dynamic duo is the main reason your blood's pH stays so perfectly stable.
So let's walk through how this actually works in real life. Let's say you're working out, right? Your muscles start producing lactic acid, and that acid starts seeping into your bloodstream. Bam! Immediately, that bicarbonate ion we just talked about grabs it, neutralizes it, and turns it into carbonic acid. Then an enzyme zaps that carbonic acid, breaking it down into carbon dioxide and water. And how do we get rid of extra carbon dioxide? Simple. You just breathe it out. It's this incredible connection to your lungs. In fact, if you hyperventilate, you're breathing out too much CO2, and your blood can actually become too basic. And if you hold your breath, CO2 builds up, making your blood too acidic. It's this beautiful, elegant system that's always adjusting to keep you right at that perfect 7.4.
But are these chemical guardians invincible? Can they go on forever? Well, not exactly. And that brings us to a really important idea: a buffer's breaking point.
This limit has a name. It's called buffer capacity.
Think of it like a sponge. It's the total amount of acid or base that sponge can soak up before it's completely saturated and the pH just starts to spill over and change dramatically. So, no, the protection isn't infinite.
And what determines that capacity? It really just comes down to concentration. A buffer that's packed with more of those guardian molecules, like this 1.0 molar solution here, is going to have a much higher capacity than a weaker, more diluted one. It's just common sense, right? The more soldiers you have on the field, the more of the enemy you can fight off before you're overrun.
So yeah, a buffer is officially overwhelmed when you've thrown so much acid or base at it that you've completely used up one half of that protective duo. Once all the weak base is gone, for example, there's nothing left to defend against any more acid. The shield is down and the pH will just crash.
So when you boil it all down, that's what buffers are. They're these invisible guardians, these unsung heroes of chemical balance. Whether it's in a science lab or, more importantly, in the blood flowing through your veins, they are constantly on patrol, neutralizing threats and protecting the whole system from sudden, disastrous changes. It's a pretty wild thought, isn't it? That right now, your body is performing this ridiculously delicate, high-stakes chemical balancing act. And you don't even have to think about it. It just happens. Which kind of makes you wonder, right? What other invisible, amazing systems are working away in the background, keeping you alive right this very second?